So this is the third part of our discussion related to metal semiconductor contacts, and hope we'll wrap it up today. And so we've seen that when you put a metal on a, let's say, an N-type semiconductor or a P-type semiconductor, we've been talking mostly in terms of N-type semiconductor. And we said that if you take silicon, for example, take any metal, aluminum, gold, silver, what you end up is getting a barrier height. You find that there is a barrier height between the metal and the semiconductor. And we saw an energy band diagram of the kind that you see over here. By now we are familiar. This is the conduction band. This is the valence band here. And this is the Fermi energy here. So what we note also, if you look at the energy band diagram, what you note here is that as you go towards the interface here, you find that the band's bending up. And we know when the bands bend up, the separation between EC and EF increases, which basically means that the electron density is decreasing. And because electron density depends exponentially on the separation between EC and EF, you know that the electron density, as you go towards the interface, exponentially decreases. Okay, exponentially decreases here. But we know that so what is happening is then as we go towards the interface, we find that all this region is getting depleted of electrons. Right? Here, if we are in this particular region here, the number of electrons is equal to roughly the number of dopant atoms, unless the dopant atoms are too large. Right? So if I have 5 times 10 to the power 16 doping, here, the number of electrons are going to be 5 times 10 to the power 16. But then as I go towards the interface, the number of electrons are going to drop, and drop very rapidly. Why? Because note that the electron density depends exponentially on the energy here. So it drops exponentially. And very soon what happens is the electron density becomes very small compared to the background doping. And so this region that you see here, this region here is what we call as the depletion region. Why? Because it's depleted of electrons. The number of electrons is smaller. And as I said, as you go deeper and deeper or closer and closer to the interface, the electron density becomes very, very small here. Okay. And for that reason, this region is called the depletion region here. So what we would like to know is what is the extent of this depletion region here? How large is it? Okay. And as you might expect that if I apply a reverse bias, we know that this region, the barrier becomes larger. This region becomes wider in width here. So depletion width will increase as you apply reverse bias. And as you apply forward bias, the depletion width will decrease here. All right. So how do we estimate this depletion width? That's the problem that we'll address. So if we look at the charge density here, charge density anywhere, by the way, will be equal to, because we have an N-type semiconductor, will be equal to Q. Now this is volume charge density, Nd plus number of ionized donor atoms, plus P0. These are the positive charges in my semiconductor, minus N0. N0 is the negative charge in my semiconductor here, right? Because we are taking an N-type semiconductor, we'll neglect P0. So charge density anywhere in my system is Q Nd plus minus N0. And for most of our discussion, we'll assume Nd plus is also equal to Nd. Okay. All right. If I look at a region like this here, this region, what happens is this region is neutral. There are no charges. Nd plus is equal to N0. Right. So the charge here is 0. If there had been some charge here, there would have been a field, and field implies that the bands would have bent. And since we see a flat band here, it implies a net charge equal to 0. So this region is pretty obvious what is happening. As we go further into this particular region, we know what is happening. Nd plus will remain same. Number of ionized donor atoms remains the same, which we are assuming it equal to the donor density. N0 is dropping sharply as you go here. N0 is dropping sharply. So now you know that rho will become positive. Rho will start with 0 here. Charge density is 0 here. And as you go in, it will start to become positive. And very soon, what will it become equal to? Practically equal to, rho will be practically equal to QND plus, because electron density becomes very small. Okay. All right. So as I said, if you apply a forward bias, we have seen the energy band diagram. The net voltage becomes smaller here. Net voltage becomes smaller here. This implies depletion width. It becomes smaller than the equilibrium depletion width here. You apply a reverse bias here. The band bending becomes even more. Note that more band bending means more electric field. More electric field means more charges here, and that means the larger depletion width here. So that is fine here. So let's look at the depletion width. As I said, we want to calculate the depletion width, and so this is the picture that is happening here. As we just said, that as you number of electrons nx will be equal to nd, and as you enter the depletion region, the electron density, we said, falls sharply here, and it doesn't become zero. It will never become zero, but on a linear scale, it appears as if it's become almost like zero here. Okay, so this is the kind of a thing that you have here. And then if we look at nd minus nx here, so nx is electron density is going like this here. nd minus nx will then go like this here. Okay, why am I talking about nd minus nx? Because rho is what? nd minus nx. We just saw, if you go back, rho is nd minus whatever is the electron density. Okay, so that's why we are talking about nd minus nx here. So this goes like this here. So that's how my region next to the interface looks like. There's a charge is, all right. So all right. So so this is then the charge density, rho equal to q times nd minus nx. So this is how your rho will also go. Rho will also go like this, except that you have to multiply it by q. Now this is a little bit complicated. As you can see here, there is a constant region, constant charge density, and then there is a transition region here. All right, there's a transition region here, and the transition region we'll see later on when we discuss p-n junction in a little bit more detail. So what we do is, as a first order approximation, we say that the charge density looks like this here. We approximate it by saying that the charge density is equal to rho q times nd up to a certain point, and then we ignore the transition region altogether. We say then the charge density drops to zero abruptly here. So that's an approximation, and if you look at this approximation, it may appear to you the approximation will be perhaps true if the transition region is much smaller as compared to the constant part here. Okay, but as I said, later on in our discussion, we'll see more as to how accurate this particular approximation is, and we'll look at the errors involved here. So right now, what we'll do is the charge density, then instead of taking it constant and then changing in a gradual manner going towards zero, what we'll approximate it as a constant and then abruptly dropping to zero here. So that's the approximation that we'll make here. So we'll assume the depletion region is a region next to the interface with a constant charge equal to q and d up to a certain point and then dropping to zero. Okay, that's an approximation. The real variation is what you see over here. Okay, so this is the depletion approximation then. Rho, as we said, rho is basically equal to P0 we are neglecting. So rho charge density becomes Q nd plus minus N0 here. And we are saying in this region here, region of width W, which is the depletion width, N0 is much, much smaller than Nd. N0 is much, much smaller than Nd, and therefore rho we can approximate it as simply Q nd plus. All right, it's a common mistake that people make. They say electron density here is zero. That's not true. Electron density in this region is not zero. All you need is electron density to be much smaller than the doping. That's all. It's much smaller than doping, and therefore I can say rho equal to Q nd plus. And as I said, this is an approximation. The region, this region is not abrupt. All boundaries, in nature, the boundaries are not abrupt. They're all gradual. Most of the time, all boundaries are gradual in nature here. But that makes the problem a little bit more complicated. Okay, and this approximation we'll see is a widely used approximation. It's called a depletion approximation, and the width that we'll get and we'll use it at various places is a fairly good estimate of how large the this region is here. A more accurate word for this region here, this region that you see here next to the interface, is not depletion region but a space charge region, which is obvious from its name. Space charge region, what does it mean? It's a region of space which has charge, right? So that's the accurate word. It's a space charge region. Now, depletion is we know that this region is depleted of electrons, right? This region is depleted of electrons, so it's a depletion region also, okay? And depletion approximation means that you can approximate it by a constant charge density here, Q and D, which is an approximation. Okay. All right. So with this approximation, now we can use Poisson's equation to determine what this depletion width is, W. Okay. So we start with Poisson's equation, which we are familiar. Del square psi by del x square. Psi is the potential, volume charge density, permittivity of silicon here, or the semiconductor here, and depletion approximation allows us to write rho equal to Q and D. Simply Q and D by ES here. So this is the equation that we have to solve. And what are our boundary conditions? One of the conditions is, note that there is no charge here in this region, and therefore electric field in this particular region is 0, which means del psi by del x, which is electric field, minus of that is electric field, at W, right at this particular point and beyond, is 0 here. That's one boundary condition. Okay, we need, it's a second order equation, so we'll need another to determine completely W. And where is the other boundary condition going to come from? One is that the electric field here is 0, fine. The other one, the net voltage drop from here to here, do we know that? What is that equal to? The built-in voltage. If I'm talking about equilibrium, note, go back and look at this diagram here. The voltage drop from here to here is VBI minus VF. So we know that also. We know VBI and we know whatever voltage we have applied. So that's the other boundary condition. Okay, so we have two boundary conditions, and therefore it's a simple differential equation which we can solve. And so let's do that. Let's integrate this equation once. If we integrate it once, del psi by del x, we'll get Q and D ES x plus C here. We put this boundary condition at x equal to W. My electric field is 0 here, so that lets me write del psi by del x Q and D by ES W minus x here. Okay, we know that electric field is the minus of this one. So the first thing that we get from our Poisson's equation, we get a value for field. What is the field inside the junction here in this particular depletion width here? So F equal to minus Q and D ES W minus x here. So field is 0 obviously at x equal to W, and we can see here field is maximum at x equal to 0 here. All right, so that's the behavior of electric field. Does it make sense? Field is negative. Everybody agrees field is negative. Why? I have positive charge on this side, on the semiconductor. Where is the negative charge? On the metal, right? So positive to negative, so field is negative. So that's fine. Field is all negative here. Field is 0. Obvious neutral region, field is 0 here. And then field starts building up. As you enter this charged region here, field starts building up and reaches a maximum value here. Where are these positive charges going to terminate? A charge from here will terminate on the electron here, right? So everybody sees now a charge from here will terminate here, a charge from here. So as you go closer to the interface, you have the maximum field lines, right? So which is the maximum electric field here. So we get this value here, and we know what the maximum value of the field is by putting x equal to 0 here. So we get the maximum field here, Q and D by ES into W here, except that we don't know W. We don't know the depletion width here, but if we knew that, we could have found out what the maximum field at the junction is. All right, let's integrate the Poisson equation once more. So we have del psi by del x Q and D ES W minus x here. Let's integrate it once more here. So we get Wx minus x squared by 2 plus C here. And this is where now, so what we get the potential, and we apply the boundary condition. So we can see here that at x equal to 0, C is nothing but psi 0 here. So we can write psi x equal to Q and D by ES plus psi 0 here. Okay, so we get that here. Psi at W at this particular point, psi at W will be equal to W is depletion width, Q and D by 2 ES, W square plus psi 0 here. And now we know the difference between the voltage here and the voltage here is equal to psi W minus psi 0 is equal to VBI minus V here. Note that if you're talking about equilibrium, you'll put V equal to 0. If you're talking about forward bias, you'll put some positive value of V. If you talk about negative or reverse bias, you'll put a negative value of V. So it's a general expression. Although the diagram is being drawn assuming that V is positive, it's a general equation here. So you put VBI minus V equal to Q and D by 2 ES W square here, and therefore you get an expression for W. What is the depletion width? Okay, so we have solved the Poisson's equation. We know what the depletion width is now. If we know doping, and we know built-in voltage. We will know what the depletion width is. And once you know depletion width, then you know electric field, you know everything about the depletion region. Okay. So very simple second order differential equation with the boundary condition that electric field is 0 at the edge of the depletion region. The net voltage drop across the depletion width is the built-in voltage minus the applied voltage. Okay, so we get an estimate of depletion width, and this is the complete diagram here. So this is the charge inside my depletion region here, Q and D, W here. We integrate, we do that field, looks like this here, and voltage. Now note that what we get from here is the voltage drop here, and arbitrarily, as I've said earlier, it doesn't really matter what the absolute values of voltages are. What really matters is the voltage drops here. So here, for example, psi 0, I've just assumed it to be 0 here, and then psi at W is that value that we've just calculated. Okay. Note that instead of doing equations, we could have also, once you know this, that charge density goes like this here, then you know that we could have figured these out by simply doing the electric field is what? We can write this same equation as this is electric field, del F by del X equal to Q by rho by epsilon S. So if you know the charge density, how do you get electric field? Simply taking the area. Right? If you integrate this particular, so you can do it graphically also. If you know rho versus X here, all you do is you take an integral of this. You start from 0 here, and you take an integral because you're going in negative X direction. That's why you end up getting a negative value here, right? So you do an integral of this, you'll get here. You do an integral of this, you'll get this particular plot here. All right. So all that you have to do is, many of these problems you can even do it graphically by drawing this here and then taking the area under the graph here. You get this here. You take the area under this particular graph and you get this particular value here. Okay. All right. So let's all do a problem here. Okay. So that you get a hang of what these Schottky barrier diodes are. Let's do this particular problem. So we have so we are talking about a metal semiconductor diode. An alternative name for this is a Schottky barrier diode. It has an electron barrier height of 0.8 eV. N-type doping is 5 times 16. What I want you to do is determine the reverse saturation current and forward voltage drop for a current of 10 milliamperes. Area equal to 10 micron by 10 micron. Permittivity of silicon 11.7 multiplied by the free space permittivity. This is the Richardson constant for silicon, 240 amperes per centimeter square Kelvin square here. All right, A star here. So what you need to do is, first thing that we would like to do is calculate currents. Okay. I know people will not remember the expression. So here is it. J equal to Js. It's a usual diode equation. J equal to Js exponent QVF by KT minus 1. Js is Richardson constant, T square exponent minus phi b by KT. And what we want you to calculate is reverse saturation current. So which is nothing but Js multiplied by area. That will be the net reverse saturation current. And we also want you to determine the forward voltage drop for a current of 10 milliamperes, which is also straightforward. 10 milliamperes here. Once you know Js, you can calculate what is Vs. The reason why I'm asking you to calculate these is so that this equation settles down in your mind. This equation is important, and also the numbers that we will get, especially for the forward voltage drop. You'll see what kind of number you'll get for Vf. As I said, the forward voltage drop is interesting for us. The number that you will get for forward voltage drop. Does somebody have a value? When you calculate the voltage drop, -1 of course doesn't matter. -1 here can be safely ignored because Vf will come out to be one thing is missing is KT by Q, all of you know, is 26 milli electron volt, right? KT by Q is 26 millivolt, room temperature. All right. Do these values make sense? Is anybody getting these values? What strikes you when you look at these numbers? You guys are familiar with diodes. What strikes you? Anything? Anything which? Look at this number. 0.517 for 10 milliamperes is a significant current, right? 0.5517. What are you familiar with? 0.7 or whatever, right? So typical PN junction diode. So one of the qualities of a Schottky diode is what? For the same current, you require a much lower voltage here. So that's one of the major advantages here. I want to show you. Hopefully, I have a data sheet of a Schottky barrier diode. What happened? Yeah, data sheet for a. I just picked from the web a data sheet for a Schottky barrier diode. Can you all read? See how they, these manufacturers, how they are selling this Schottky barrier diode. Look at that. Schottky barrier diodes are designed for high-speed switching applications, which we'll see later on. Note what they say: extremely low forward voltage. Extremely low forward voltage. That's one of the key characteristics of a Schottky barrier diode. Very low on voltage here. And in their case, if we go and read what their on voltages are, you can see that they note that for 1 milliampere, note the data sheet, 1 milliampere current, a forward voltage of 380 millivolt. So you can get 1 milliampere current with only 380 millivolt drop here. And for 10 milliamperes, they get 500 millivolt, which is what we are getting, roughly about 510 or so millivolt for a 10 milliamperes current here. So this is one of the characteristics of Schottky barrier diode, that for the same current, you'll get a much lower voltage drops here. And the other main characteristics, which you'll appreciate later on when we do PN junction, is this part here. They are high-speed diodes. So these are the two places where Schottky diodes are frequently used. When you want high-speed switching, rapidly, when you have signals which are rapidly varying, you use Schottky barrier diodes. And when you require very low voltages, you use Schottky barrier diodes. Okay, so that's the characteristics here. This is one part. Let's do one. So low voltages here. Let's do another calculation here. Let's calculate the depletion width at equilibrium. Okay, so we just calculated currents and voltage drops. Let's calculate the depletion width. Depletion width, let me give you the formula. W equal to 2ES QND VBI minus V. And VBI, you should learn how to calculate VBI. VBI is equal to the barrier height minus phi n. That's VBI. Phi n is KT, ln NC by N0. And N0, of course, is going to be simply 5 times 10 power 16 here. So I've given you the VBI, built-in voltage, but please note how one calculates built-in voltage here. Once you give the barrier height, phi b, and once you know the doping, you know phi n here, and the difference between phi b and phi n you can see here is built-in voltage here from the energy band diagram here. So that's the built-in voltage for the Schottky barrier diode. Depletion width is here, 2ES by QND VBI minus V here. So let's calculate the depletion width at equilibrium. And the important thing is, again, what is a typical value for a depletion width? Of course, depletion width would vary with the value of doping, but a number to keep in mind, okay, for depletion widths. So let's do that calculation. NC people remember? How much is NC? Huh? Order, at least order you have to remember. 10 power? No. In what? In centimeter cube or meter cube? Centimeter cube, no. 10 power 21 is wrong. 19. For silicon, let's keep that number in mind. 10 to the power 19, 2.8 into 10 power 19. So 10 power 19 is a number that you all must keep in mind at least. 2.8 you may forget. So 10 power 19 is the density of states. See, when you start working with these devices, numbers are important in order to arrive at some, various conclusions. Barrier height 0.7 is a typical number. 0.7 electron volt is a typical number. Doping is here. Built-in voltage for Schottky barriers are lower. 0.635 is sort of a typical number. All right. Depletion width number is okay. 1282. So what is the number to keep in mind? 1000 angstrom. 1000 angstrom depletion width for a doping of around 5 times 10 per 16. 1000 angstrom is what you need to keep in mind. And obviously, depletion width depends on voltage applied. So let me give you now, these numbers are, look at what happens, minus 1 volt. Depletion width becomes 2000. 2057 angstrom at minus 1 volt. So depletion width obviously increases as you make the voltage negative, reverse bias. And depletion width is 592 angstrom at 0.5 volt. Okay, so the numbers that you can see here, about 1300 angstrom here, 2000 angstrom here, 592 but close to 600 angstrom here. Okay. All right, so we are calculating all of these things here. How do we know that they are correct? How do we know our theory is correct? How do we know that the formula is correct? Right? That this is really the depletion width. Huh? Measure it, right? How do you measure depletion width? Huh? Resistivity will not do it. Okay, so let's look at that. What is one implication of depletion width? Okay, how do we? So as I said, throughout this particular course, as much as possible, whatever formulas and all that we'll put, we'll also ask how can we measure? How can we find out whether this is correct? You know, how well does it match with theory? So how do we measure depletion widths and what all can we do here? So note that what I have done is the following. I have an N-type semiconductor. I have put a metal here, and this metal here forms a Schottky barrier diode. At the bottom, I'm calling it's also a metal, but we'll just see towards the end of this particular lecture, we are calling it sort of an ohmic contact. It's a special contact. There are hardly any drops here. Okay, it's like you can think of it like an ideal contact here. Okay, so this is a Schottky barrier diode. We know that in a Schottky barrier diode, we're going to have depletion width. This region is going to be depleted here, right? Let's say I've applied some voltage, say reverse bias of minus 1 volt or whatever. There'll be a certain depletion width, right? The green region shows depletion width. Now suppose, let's say this is the reverse bias voltage here. If I increase the reverse bias voltage by a small amount, what will happen? Depletion width will increase by a small amount, right? So let's do that. Let's increase. So keep in mind, this is reverse bias voltage for us. Okay, so we increase it by a small amount. Depletion width will increase by a small amount, right? In the process of increasing depletion width, what has happened? What do I mean by the fact that depletion width has increased by this much amount? Earlier, what happened to the electrons here? See, earlier this region, yellow region that you see here was neutral, right? Now what have I made? I've made positively charged. So what happened to the electrons here? So what we did was, when I applied negative voltage, what do you need here? When you apply negative voltage to a metal, what do you need? Extra negative. You need electrons, right? So what happens is you took the electrons from here. These electrons were pushed. They went to the ohmic contact. They came to the ground here, and the circuit is completed here, and they came and sat here. Okay, so this is what is happening here. You get an extra positive charge here, right? Because of the depletion region, Q and D. And those electrons that were pushed out, they went in, away, and they come and sit over here, right? So you applied an extra voltage of delta V. What happened? You created an extra positive charge here and negative charge here. What does it look like to you? A parallel plate capacitor, right? A parallel plate capacitor, positive charge here, negative charge here, separated by how much distance? W. So what is the capacitance then? Can I write this? Parallel plate capacitor epsilon S, because of permittivity of this whole region here, divided by W, multiplied by area. So this whole thing manifests itself as what? As a capacitance. So I can actually take my this Schottky barrier diode and take a CV meter and measure the capacitance. And once I know the capacitance, and I know how much area of my Schottky barrier diode is, thereby I have my depletion width. So direct measurement of what depletion width is through measurement of capacitance. And that tells you what the value is. So, whatever number I was quoting, you can actually go ahead and measure capacitance and it will correlate very well with that particular number there, Cj with this. Okay. And we can take the expression for W, 2Es by QND VBI minus V here. We can take this and plug it here into this and we get an expression for capacitance. So all Schottky barrier diodes will have capacitance given by an expression like this. Okay. And you can note that as you apply reverse bias, depletion width increases, capacitance decreases here. So you have a variable capacitance also. You have a voltage dependent capacitance available to you here. Not only that, this is so how should I think about my Schottky barrier diode? Well, I should think of it like this here, a circuit model. Eventually you'll have to use a Schottky barrier diode in a circuit. So think of Schottky barrier diode as a current source. Is not really a current source, but a current here in parallel with the capacitance here. What is this current? Current we have already seen. I equal to Is exponent QVF by KT, and this one here in parallel with a capacitor here, capacitor given by this this expression here. So that's how you should think of Schottky barrier diode. With this current, when you forward bias it, of course you'll have significant current. When you reverse bias it, then this term becomes negligible. You'll have very little current here. A Schottky barrier diode simply behaves as a capacitor in reverse bias because the currents are very low and it's simply a capacitor with a value given by here. While in forward bias, you'll get a current. In addition, you'll get a capacitor in parallel here. Now, if you're wondering why have I put capacitance in parallel, think about it. We'll come back and answer it later on. Yeah. I mean, if not in parallel, where else can it be? Can I put it in series? Doesn't make sense, right? Series, if you put a capacitor, then how will that current flow, right? But so that's a trivial way of answering that. I have two ways of putting a capacitance, either parallel or series. Series I can't put, it will block my DC current. So I can only put it in parallel. Okay, that's maybe a trivial way of answering. But another way of answering, think about it, why in parallel? Okay. All right, Schottky diode is a very good test structure. What do I mean by test structure? See, test structure for, see, if you look at this numbers here, you see doping. So for example, I've taken a semiconductor, I put some doping into it. How do I know how much doping do I get? How much doping is actually present? We saw earlier how many electrons are there by using Hall effect, right? You are seeing a term here, VBI. How do I know what is the built-in voltage here? Schottky diode is an excellent test structure for measuring these things here. What do? Well, you have a N-type semiconductor and you have some ohmic contact at the back and you want to know what the doping is. Okay. So what you do is, if you want to know what the doping is, just evaporate. You can take your N-type semiconductor, evaporate some aluminum on top of it. Okay. So create a Schottky. The moment you put aluminum on N-type silicon, it becomes a Schottky barrier diode. Right. So it's a Schottky barrier diode. Measure the capacitance between here and here. Which means, and we know, we've already verified that this expression is correct. So you measure the capacitance between here and here. All right. So Cj is what you measure. Area you know, because you are evaporating this particular metal on top of the semiconductor, you know the area. So if I take this equation and I write it as area divided by Cj square, I get 2 by QES ND VBI minus V. And what do? I measure this capacitance that you see here, or this capacitance that you see here, for different values of reverse bias voltage. I measure one value of capacitance for one reverse bias voltage, another value for another reverse bias voltage, and I measure it for 4, 5 reverse bias voltages here. And what do I do now? Area I know, Cj square is measured, V is, instead of V, what do you write now? Plus VR. Okay, because it's reverse bias voltage, so you make it plus VR and you plot this out. Okay, I've normalized by area here. So area I've ignored here. Say area is 1 centimeter square. And so 1 by Cj square. Plot it versus VR. What does this intercept give you? Built-in voltage. So there you have actually measured the built-in voltage of your Schottky barrier diode VBI. What does the slope give you? 2 by QES ND. So you know permittivity of silicon, so you can measure what the doping is. So thereby, it's an excellent tool that all you need is just evaporate metal on top. You form a Schottky barrier diode, measure the capacitance, and plot 1 over Cj square versus voltage here, and thereby you end up calculating two very, very important quantities: the doping, you know how much is the doping, and you know how much is the built-in voltage here. So you measure both of these things here. And note that once you know the built-in voltage, what do you know? So I can determine doping, and I know built-in voltage. Go back to this expression. What is built-in voltage? Phi B minus phi N. Once you know the doping, do you know phi N? And so what can you measure? The barrier height. The Schottky barrier height also you get. Right? So many interesting things you're getting through a very simple measurement. All you need to do is deposit metal and measure the CV, capacitance voltage characteristics. And thereby you're able to get built-in voltage, you're able to get doping, you're able to get barrier heights. All of these things you can get through this particular test structure here. Okay. All right. Let's come back now. But there is trouble for us. And the trouble for us is the following. We said, remember when we were talking about contacts, that suppose I'm making a resistor, that I want to make a contact here, I want to make a contact here, and I want this whole thing to act as a resistor. Now, in this case, we don't want drops here to be large. You know, a drop here and a voltage drop here to be large. We want the drop, all the voltages that you apply. So in this case, we are not interested in Schottky barrier diode. All we want to do is, we have an N-type semiconductor, we want to make a contact to it, and we are interested in the property of the N-type semiconductor, right? So we don't want any voltage drops to occur here, we don't want any voltage drops to occur here. Whatever voltage we apply, we want it to apply in this region, right? So in that case, we have seen earlier that for current flow, for a contact, one of the important properties are the contact resistivity. We started a discussion in metal semiconductor contacts by defining contact resistivity, and we defined as rho J by rho V at V equal to 0 here. And we said we want very low values of this contact resistivity. I don't know if you remember a value that we wanted. We had said, we had looked at a PN junction and we had calculated a value of rho. What kind of a rho do we want? And the number was 10 to the power minus 6 ohm centimeter square. That was the number that we want. Otherwise, what happens is the properties of your device, they start being determined by the contact rather than by the PN junctions and the dopings and all of that here. Okay. So now, if I take aluminum, let's say, and deposit it here, we know that it forms a Schottky barrier diode. If you simply take a metal and deposit it on a semiconductor, it forms a Schottky barrier diode. And Schottky barrier diodes characteristics is like this here. J equal to Js exponent QVF KT minus 1. And we just calculated a typical value of Js as 10 to the power minus 6 ampere per centimeter square. So now if I calculate the contact resistivity by simply taking a derivative at V equal to 0, we find contact resistivity as 10 to the power 4. So this is a big problem for us. That I'm not interested in a Schottky barrier diode. I'm interested in forming a very good contact with very low voltage drop. For that, I require a rho value, a contact resistivity of 10 power minus 6. But if I simply take a metal like aluminum or gold and I deposit it on N-type silicon, I end up getting rho which is very high. Very, very high, which means that all my properties will be determined by the contact rather than by the device. So this is a trouble because you are forming a contact just for applying voltages and extracting current. You don't want voltages to drop here. But for that, you require rho of 10 power minus 6. And simply putting aluminum is giving you 10 to the power 4. So what do you do? Well, what people do is the following here. We just calculated, note now the idea here. This is a very important idea. We calculated depletion width for 5 times 10 power 16, which was equal to 1282. I gave you the formula, we all saw that. Now suppose I start increasing doping. 5 times 10 power 17, the depletion width becomes 424. Go back and see depletion width expression here. Where do we have? Depletion width, right? 2Es, Q and D. Inversely proportional to doping, right? Okay, so let's start calculating the depletion widths here. 5 times 17, depletion width is 424. 5 times 18, depletion width is 140. 5 times 19, depletion width is 46 angstrom. What it means is if I dope it very, very high, depletion width will become very, very small. Now, this is what is very interesting. I can't go into the details of it, but think what is happening now. Low depletion width, my barrier height remains the same. Low doping, depletion widths are large like this here. Okay. High doping, depletion width is very, very narrow here. And you can see here, conduction band is merged with EF. High doping means what? EF is very close, right? It's almost merging with EC here, right? So EC here is merged here. So you have two pictures here. One is low doped Schottky barrier diode, depletion widths are large, and another one is very highly doped Schottky barrier diode here, right? So now let's see what happens as a result of doping here. Of course, depletion width has become large. Let's take a case of low doped Schottky barrier diode. How does current flow? If I have an electron here, the electron goes here and goes over and comes here, right? That's what happens here. That's the thermionic emission part here. In this case now, let's start with an electron here. It starts here, just goes through the barrier. Why is it able to go through the barrier? It's extremely thin. And I can't go into the details, but there's a quantum mechanical tunneling process here. So tunneling comes into picture. Tunneling is very, very sensitive to the thickness of the barrier. It's not going here. You may be wondering why it doesn't start from here and go directly here. Well, why? Because it's very thick. It's extremely thick. We just calculated at 5 times 10 power 16. The barrier thickness is how much? 1000 angstrom. Tunneling is exponentially dependent on thickness of the barrier. So it's not able to tunnel. It can't go from here to here. So it has to go then over the barrier here. But once you make it very thin, it starts from here and just goes here. So note that now electron, even though this large barrier is there, electron has no problem. It can just start from here and just move, right? It's as if the barrier has become transparent. It just moves in through here. Not only that, an electron can start from here and then just go here. So now what is happening is either way the electron can go, from left to right or from right to left. How did we do that? By making it heavily doped. Heavily doped, the barrier becomes extremely narrow here, and then tunneling process starts to occur here, and then now you are able to get very low contact resistivity. So that's the trick that people use for making a very good contact. So if you keep doping small, it acts like a Schottky barrier diode. If you make doping very, very high, it's as if the contact has become transparent. Carriers can easily go back and forth. And therefore, you start to get something which behaves like a close to ideal contact here. Okay. So that's why whenever you see a device, let's say you want to take an N-type semiconductor and want to use as a resistor, what do? You deposit aluminum, but underneath aluminum, what do? You create N+. N+ means what? Very high doping. And you create N+, very high doping. And thereby, this whole thing acts as a very good contact with very little drop here. This whole thing acts as a very good contact with very little drop here. And now, where do all the drops occur? They occur across the N-type semiconductor. Okay, so that's why everywhere that you will see in semiconductors, wherever you want to form a very good contact, you will find under the contact, there's very high doping. Very high doping. If you want a P-type contact, you would have made P+. If you want an N-type contact, you make N+. And that's how you make a contact which is very good. So very high doping is the trick. You make the barrier very narrow, and the electrons are able to tunnel back and forth, and thereby provide small contact resistivity. Okay. Note two things happen by doping it very high. One is that rho c becomes very small because of tunneling, and also the sheet resistance under the contact also becomes very low. So overall contact resistance then becomes very small through this means here. All right. Okay, look at this particular picture here. What do we see? Two kinds of contacts. What will this be? It's like a good contact, ohmic contact. We will call it an ohmic contact in the sense that very little voltage drops here. And this will be a Schottky barrier diode here. Will there be a depletion width? Yes, right? If I apply a higher voltage, what will happen to depletion width? Will increase. Can you think of an application of this phenomena? This is like a semi-insulating substrate, doesn't play a role. It's just a substrate, right? It's like a undoped, a very high resistivity substrate here. Can you think of a, by the way, if I apply a higher bias here, depletion width increases, the electrons are pushed out. How do they come to the metal? They are pushed out, they go here, come here, through the ground, and they come over here, right? So this provides a contact now. I don't need a contact here. I can form a contact at the top. So as you push the electrons out, as you increase the depletion width, they go here and they come here. Look at this one now. This is the basis for a very important transistor called MESFET. Metal semiconductor field effect transistor. Can you see a transistor here? What do you need for a transistor? What do you need for a transistor? That the current between source and drain should be altered by a third terminal, which is the gate, right? You want transconductance. Will we get a transconductance? Will a voltage here alter the current flowing between source and drain? Yes or no? Everybody sees that? Say I apply negative voltage and a positive voltage here. So if you apply positive voltage, forget about this for a moment. If you apply positive voltage, what will happen? Electrons will start from here. This is a good contact, so there'll be very little voltage drop here, flows through the N-type semiconductor, and then will come here, right? So that's the path of the current here. Except that there'll be a depletion width here, right? So the whole region is not available to you because the gate is a Schottky barrier diode. There's a depletion width here. Why is the depletion width larger here? See, the voltage that you see in the channel, say you apply 5 volt here, is 5, 4, 3, 2, 1, 0, right? So higher voltage drop here, and therefore depletion width is. Now if I change the gate voltage, will the depletion width become higher? And thereby will it alter the current flowing between source and drain? Right? You can see here, and thereby that's the basis for a transistor called metal semiconductor field effect transistor, MESFET. This is widely used for transistors such as gallium arsenide and a number of 3-5 semiconductors. The reason being is that it's difficult to grow oxides on these kinds of semiconductors, so you can form a field effect transistor by simply using a Schottky barrier here. All right, so let's stop here.